Hello everyone, Assalamu alaikum. I am Muhammad Mahirur Rahman from Bangladesh University of Engineering and Technology. I will be presenting you our paper, Analog Signals Processing Based Hardware Implementation of a Real-Time Audio Visualizer. Our whole presentation is divided into 4 parts: objectives, design and implementation, results and analysis, and conclusion and future work. So moving into the objectives part, I will be showing you the 5 objectives of our work. Is that we have tried to showcase the applications of signal processing in the field of entertainment, and we'll be showing you the development of a real-time audio spectrum visualizer using analog signal processing circuit, and then we'll be showing you the implementation of our work in a 12-storied building with where lights were arranged in 10x8 matrix blocks, and then we'll be showing you the audio signal input from live stage performances taken, and how the signal was processed into different stages, and then we will be showing you the processing stages, results and implementation in details. So helping you thoroughly understand our work, here is the flowchart of the whole system. The first of all, audio signal is taken as input, and then it moves into the amplification and active filtering stage, and then it moves into the rectification and passive filtering stage, and then it moves the signals move into the comparator block, and then to the AC switching block, and finally the signals from the AC switching block are used to turn on and off lights, where we implement the visualizer. And then we move into the design and implementation section, where we see the block diagram of the whole system. We divided the whole block diagram into different parts, and we'll be explaining it in details to make you understand what work we have actually done. So giving you a slight idea, we have taken the audio's input, divided into 8 bands of frequency, and for each band we have implemented 10 blocks of light in the vertical axis, and the frequencies were in the horizontal axis. So moving into the pre-amplifier section, here we have kept provisions for both large signal and small signal input. If the signal is small, then it moves through an open based amplifier, and also a gain control knob, where we can use it to control the gain of our signal. And for the large signal input, it has the provision to bypass the whole amplifier section. And also, if the large signal is very large, then we can use another gain control knob with less than unity gain. So from this section, the signal is passed into the active filter section, where we have implemented 8 active filters, consisting of a low pass filter, a high pass filter, and 6 band pass filters. We have ensured that the roll off is steep, so we used second order Chebyshev filters, and steep roll off was necessary to ensure minimum overlapping of frequency within each band. More on filters we'll be discussing in the results and analysis section, where we'll be showing you the simulation that we have done. So, and our frequency band was splitted between 0 and 6000. Frequency bands above 6000 was also included, but the choice was due to accommodating the different frequency range of different instruments that were being played in the live music performance. And from this, the signal from each band, since it's divided into each band passes into the precision rectifier block, where we do a full wave rectification on the audio signal, because DC component of the bandwise separated monotonic audio signal is necessary. And for each 8 bands, 8 rectifiers are there, all operating in the same way. And we used full wave rectification to minimize the signal loss through diode if we would have done half wave rectification. So from here we move on to the quantitative analysis of the signal. Qualitative analysis was already carried out in the band separating in the active filtering stage. So from the full wave rectification section, the signal is moved on to the low pass filtering section where LC filters were used, and the frequency components from the rectified signal were divided and eliminated since it interfered with the power signal and also it caused flickering of lights. So by implementing this passive filter, we eliminated the flickering problem, and also we had an added advantage is that by varying the parameters of the passive filters, we can determine the fall time of the signal, which adds to the visual impact of the visualizer. So it compensates to the slow response time of the visualizer lights and also stops any possible flickering. And from each band we did precision rectification, and then it moved on to a low pass filtering stage, and finally it moves into a comparator switch and load block. In the comparator switch and load block, moving into the comparator block, each frequency band is now divided using its amplitude into 10 vertical blocks, and for 10 vertical blocks we have 10 comparators in each comparator block. So here 1 voltage drop across each comparator was achieved using a resistor divider network, and the comparators operated in the non-inverting operation mode, and the amplitude of the rectified signal determined the level up to which the comparators would latch the signal, and from this the decision was sent into the switching circuits for vertical axis plotting. So from each comparator block 10 signals, from each comparator block 10 signals move into one AC switching block, and according to and for one comparator we have one AC switch. These AC switches just turned on the specific blocks of the light. So if we have amplitude that reached up to 5 comparators in a comparator block, then 5 switches would be turned on in the AC signal switching block, and thus 5 blocks of light would be eliminated. So and in the AC switching block we have implemented zero crossing detectors to minimize power loss and harmonics, and also optical isolation was ensured for safe handling. And thus from this AC switching block, finally all the signals moved into the Christmas light implementation, that is the whole implementation on the EC building. So here's a small video to help you visualize it better. The music was taken as the input music was from a live stage performance in a program of Electrical Day Festival in EC building at Buet. Now moving into the results and analysis section. In our results and analysis section we report the data acquisition and also the implemented circuit. So as we have mentioned earlier that we had used one low pass filter, one high pass filter, and 6 band pass filters. So the frequency bands that were divided were 0 to 160 Hz, 160 to 400 Hz, 400 to 720 Hz, 720 to 1200 Hz, 1180 to 2000 Hz, 2000 to 4000 Hz, 4000 to 6000 Hz, and all frequencies above 6000 Hz. So second order Chebyshev filters were used, which had a steep roll-off of 40 dB per decade. For the high pass it was plus 40 dB, for the high pass it was plus 40 dB per decade, and for the low pass it was minus 40 dB per decade. And some aliasing was still present, but that were below the 3 dB cutoff, and those were not so significant. And if we show you the simulation results, we see that for the 0 to 160 Hz block for the low pass filter we achieved 159.256 Hz, which is very close, and similarly we achieved very close values for the band pass filter and also for the high pass filter. The implemented circuit is shown here, which we show you by dividing into different parts, where the comparator blocks, AC switches, and connections to the load are seen, and also the audio input block is shown, the passive filtering block is shown, and the full wave rectification part is shown. So that is what from the results and analysis section, and finally we move into the conclusion section. Summarizing our whole work, we have developed a real-time audio visualizer which demonstrated an exemplary use of hardware-based analog signal processing for the sole purpose of entertainment. But the analog signal, we have used an analog circuit design procedure. It removed the use of using high-precision digital signal processors, which are costly, and thus we provided a low-cost solution to audio spectrum analysis. Our work, apart from entertainment applications, can also be used for providing sophisticated local solutions, especially in the biomedical research arena, by using EEG, ECG, EMG signals, and our system can also detect EM interferences and also remove audio signals. So a greater impact can also be seen in observing the influence of different noise in a continuous time signal, and thus by observing that we can provide ways of suppressing them. And so finally, moving on to the future work, what can be done? What we thought of is that we can increase another dimension to our system, which is time. So time and frequency time can be in the horizontal axis, frequency can be in the vertical axis, and the amplitude can be shown as the color of light. Cold color symbolizing the low amplitude and warm color symbolizing high amplitude. So with this three-dimensional system that have not been implemented, obviously because of the challenges of cost, so we are trying to find a low-cost solution because this is costly, because RGB LEDs are necessary, which is very high cost, which is far more expensive than Christmas light box. So a viable alternative needs to be found. So that's all from my presentation. Thank you very much for being with me, and if you have any questions, please let me know. Thank you very much.